Space and its secrets have been the source of many questions for centuries. To answer them, one must leave the comfort of the Earth and face, among many threats, an invisible and particularly hazardous one: radiation. Understanding space radiation is critical for the future of space exploration, and the first destination is the Moon. But how can our neighbor be so close to us and be so drastically different? Unlike Earth, the Moon has no protective magnetic field or atmosphere. It's constantly bombarded by high-energy particles from space called cosmic rays, and occasionally by particles coming from the Sun called solar energetic particles, among other sources. Galactic cosmic rays, also known as GCRs, come from outside our solar system, created by distant supernovae. They are incredibly fast-moving at nearly the speed of light. Their particles can travel across the universe for millions of years before colliding with the Moon or an astronaut's body. Then there are solar energetic particles, also known as SEPs. Unlike GCRs, SEPs are unpredictable. They are associated with violent explosions on the Sun, solar flares, and coronal mass ejections. This can send deadly waves of radiation towards the Moon in just minutes. Astronauts caught outside without an efficient protection during one of these storms could receive a radiation dose equivalent of hundreds of chest X-rays in just a few hours. But what does this radiation actually do? Well, at high doses, it can damage human DNA, increasing cancer risk, which, for long-term missions, is a serious concern. But it's not just humans. Radiation can also affect spacecraft electronics, corrupt data, and even weaken materials used in spacesuits and spacecrafts. I'm developing a new lunar radiation model called the LERAM, that stands for Detailed Lunar Energetic Radiation Environment Model, based on an existing Mars model, the MERAM. Using powerful computer simulations with GM4, the goal is to be able to track how radiation behaves on the Moon. This will help scientists plan safer missions, design adapted spacecraft shielding, and even assess health risks for astronauts. This research isn't just theoretical and has foreseeable applications. ESA projects such as the Lunar Gateway, the Orion spacecraft with the European Service Model, and the Heracles lunar lander, among others, can take advantage of this model. By using programs like the LERAM, we can study the safest landing sites, plan habitats, and reduce radiation exposure risks. Space exploration is entering a new era. The Moon is the next step, but radiation remains one of the biggest challenges to overcome. With models like this, we are equipping scientists and engineers to plan safer missions, protect astronauts, and pave the way for long-term space exploration. One day, humans will live and work on the Moon, maybe even travel to Mars. And the work we do today, understanding radiation, designing better shielding, and predicting risks, will make that future possible.